Okay, ladies and gentlemen, good morning and welcome to the last one that we will do in AP Chemistry. And this is called the Nernst equation. And it is going to ask the question, sorry, if parts of a cell are aqueous, which we know some of them are because it is aqueous, because we know that a cell has some parts of it in solution. We have a solid electrode. The anode undergoes oxidation. It loses electrons. That's the source of electrons, and produces an ion that's in solution. So if parts of a cell are aqueous, the question we want to ask is how does concentration, affect the cell potential, what we know of as E. So welcome to something called the Nernst equation, and it is going to look awful. The Nernst equation looks like this. We are going to treat our cell potential under standard conditions. And so every time we see that little circle, that little degree symbol, it means standard conditions. Okay? We are going to take our cell potential under standard conditions, which would be the cell potential that we would find any other way, and we are going to subtract from that this monster, 0.0591 over n times the log of our old buddy Q. You know that this is going to be moles of electrons, and this guy Q is the ratio of products to reactants at the beginning. Okay, so let's assume that under standard conditions over here, my pen doesn't write consistently, that under standard conditions we are going to assume 25 degrees Celsius, 1 atmosphere, and that's not really going to be a consideration here, and 1 molar solutions. So basically we're asking if the concentration is changed, how does this affect cell potential? And you can probably guess that as the concentration decreases, our cell potential also decreases. Let's try one. So here we have a simple reaction. Okay, let me make that a little bit bigger. Okay, we have a standard cell potential of 0.48 volts for this reaction. Okay, our aluminum is our anode. It is the source of electrons, and our magnesium is the cathode. It is where the electrons are going. We're not going to worry so much about the direction. What we are concerned with is the products and reactants. Now, in this particular reaction, it's really simple because we know that aluminum here is a product and manganese here is a reactant. So our value for Q will have the concentration of aluminum over the top of the magnesium, or excuse me, manganese. Okay? Now, the only thing that you have to be careful of is you've got 3 magnesiums, which are absorbing 2 electrons each, and 2 aluminums, which are each donating 3 electrons. So we want to be careful how many electrons are being transferred. So in this case, we know that N is going to be 6 electrons, and Q is going to equal the concentration of aluminum 3 plus over manganese 2 plus. All right. We already know the standard cell potential. That won't always be the case, but in this case it is. So let's set this up. What is our new cell potential going to be if we know the standard cell potential minus my pen 0.0591 over n log Q. I was teaching my general chemistry students about log last night, and we got to watch some Ren and Stimpy, so that was fun. So let's plug everything in. Now, this one's going to be a tricky one because we have increased our aluminum from standard conditions of 1 molar, but decreased our manganese. And you could say that, well, all right, there is a stoichiometric relationship going on here, but I'm not really in a position to try to estimate. So if I had to guess, I would say that the voltage would be slightly lower because you're going to be multiplying the consideration of this by 3. I mean, there is, of course, a coefficient here and here. So we should include that here. Our aluminum with a charge of 2 plus, that'll be squared, and our manganese with a charge of 3 plus, and that will be. So you want to be careful with the concentrations of your reactants and products. All right, so we could make this a little easier on ourselves. Let's just calculate this Q out right here. We know the aluminum is 1.5 molar. That's going to be squared. The manganese is going to be 0.5 molar. And that's going to be cubed. So let's just get our value for Q right here. We'll plug it right in. Here's my fancy schmancy calculator. So we're going to take 1.5 and we're going to square that, and we will divide it by 0.5, which we will cube. We get 18 is our value for Q. So let's plug this in. If we know our original cell potential was 0.48 volts, we are subtracting this entire value, 0.0591, over 6 electrons, remember, 6 electrons being transferred, times the log of Q, which we just calculated to be 18. Okay, let's do it. We're going to do this whole big monster. So we'll take 0.48 volts, and we will subtract from this. And I'm going to do this a little weirdly. We'll say 0.0591 divided by 6 times the log of 18. See what we get. 0.467. Oops. We could round that up to 0.47 volts. So our new voltage is slightly less when we change these concentrations. Okay? So that's all we're doing. Be careful to count up the number of electrons properly, and also be careful that you are including your exponents, which I didn't do on the first example here. All right? So Q is just like it's always been, way back in chapter 13 on equilibrium. All right? And you only have, 2 compounds in solution, so calculating Q is pretty easy. And if the reaction doesn't specify which is which, you'll need to determine which is the anode. That will always be the one that is the source of electrons, and that is going to be the product because that's where the electrons are coming from. So that's going to be the one that's in solution on the product side. And of course, you'll need to know which is the cathode, where the electrons are going. That's the one that starts in solution on the reactant side and becomes a solid on the product side. All right? So take it for a spin, and good luck.